Hi everyone. So today we have Clément Bonnerot, who is assistant professor at the University of Birmingham and who will be presenting his work on tidal disruption events. Go ahead, Clément.
All right. Yeah. First of all, thank you for giving me the opportunity to present my work here and also organizing this seminar series that I think is very interesting. So yes, today I'm going to talk about tidal disruption events. And so tidal disruption events happen when a star, as you can see in the background image, gets too close to a supermassive black hole and gets destroyed by these tidal forces. And as a result, some mass gets stripped from the star, fuels the black hole, and it leads to the emission of a powerful electromagnetic signal that we can detect from Earth. So this, in particular, I will present recent progress in the understanding of the evolution of the gas strip from the star, in particular how it forms an accretion disk around the black hole, because it's really from this accretion disk that the emission that we can detect is limited. So this is work that I've been doing in collaboration with several people, most importantly, the three listed here, Wendy, Phil Hopkins, and Mark Besser. And before I start, I also want to ask that if you have questions, feel free to interrupt me at any time. I personally prefer that it works like this, and ask of all, and it's also like this. Feel free to. All right, so I'll start by explaining why tidal disruption events are interesting phenomena. Perhaps the main motivation is the following. So it can be essentially the main motivation is that tidal disruption events can probe supermassive black holes that cannot be, observed in any other methods, and it can be seen from this plot here that is showing essentially the number of supermassive black hole per bin of mass, also called the supermassive black hole mass function. So here the black line is showing black hole mass measurements that are made with methods other than TDEs, in particular using the electromagnetic emission from distant quasars, and also using the motion of stars or gas around nearby supermassive black holes. However, these methods start to become unreliable for masses less than about 10 to the 7 solar masses. And this is the range of masses that can be probed by tidal disruption. So here the upper mass limit is given by the condition that if the black hole is too massive, then the event horizon of the black hole is larger than the tidal radius, which is the typical radius at which the star gets destroyed, and as a result, the star basically enters the event horizon of the black hole before being destroyed, and therefore the TD is undetectable. And this lower mass range is more arbitrary. It mostly depends on whether intermediate mass black hole exists. So in principle, it's possible that this range extends to even lower. Right, and this range of mass is important also because it allows to potentially put constraints on the origin of supermassive black holes. And in my simplistic picture, there are two main of such mechanisms. The first is the formation from primordial stars in the early universe, also called population 3 stars. So starting from this seed black holes and evolving them to the current time, the predictions are that most galaxies, even all galaxies, even the lowest mass ones, would be occupied by a supermassive black hole. And this is also referred to as high occupation fraction. And so on the plot on the left, this would reflect by a line that just continues to increase to lower and lower black hole masses. This is the red dash curve here. And the other model is instead assuming that the black holes form still in the early universe, but from now the direct collapse of very massive clouds of gas. So the conditions for this collapse are likely to be less easily realized. And as a result, when you evolve these seed black holes to the current universe, now only a fraction of galaxies is occupied by supermassive black holes. In fact, only the most massive galaxies, while low mass galaxies may now host black holes. So still looking towards the left, the black hole mass function in that case would look something like this. Those are only approximate curves. But the most important fact is that there would be a drop towards low mass black holes. And the important thing to see here is that these two theoretical models, their predictions diverge in exactly the range of supermassive black hole masses that can be probed by tidal disruption events. And so if we can use TDs to measure black hole masses reliably, we can use these observations to put constraints on the origin of supermassive black holes. So this is one motivation, but there are also other motivations such that that tidal disruption events can be used to probe the physics of accretion and relativistic jets, because basically they are really quickly evolving systems where you can see the formation of the jet, the evolution of the jet, and the shutdown of the jet in just a few years, which is not possible for longer-lived systems such as quasars and active galactic nuclei. Right. So now a bit about the future. So what I want to convey here is that we are really at the dawn of a golden observational era for tidal disruption events. And this can be seen from this plot that shows the number of TDs as function of discovery year. So historically, the first TDs were discovered sometime in the late 90s with an X-ray telescope called ROSAT. And throughout the 2010s and 2020s, there has been a steady increase of the number of detections, in particular thanks to the Zwicky Transient Facility, but also many other surveys. This one is an optical survey. And we are now here, and in the next year, starting next year, the Rubin Observatory will come online. And the predictions are that this telescope will detect about 1,000 TDs per year, therefore increasing, as you can see in the red curve, our detection sample by about two orders of magnitude. So this is really a bright future for the field. So the goal is really to be able to build a reliable model to be able to interpret optimally this wealth of observations. Right, so what TDs look like observationally is like this. So this is showing different light curves for different TDs. And you can see that they share common properties. The first is that they last about a month, all of them. And their peak luminosity is in between 1044 to 1043 to 1044 arc per second. And finally, as you can see on this right-hand plot here, which is showing the light curve for a single TD, but in several bands, X-ray, UV, and optical. TDs are really multi-wavelength events. And here I will focus mostly on the two main ones, which are the X-ray and optical components. And even for these two components, there's a wide range of variability, with some TDs showing only X-ray, some only optical, and some both. Is there any question until here? All right. Then I'll move to, so the goal really from this observation that the large number expected in the future is to be able to first build a model that can reproduce these observational signatures, and later on ultimately to use observations to be able to constrain the properties of the system, in particular infer the black hole mass or black hole spin from the signal detected. All right, so now I'll move to the explanation of how the gas evolves during tidal disruption events. So essentially, the story starts from a star that has been scattered after many encounters with other stars at large distances from the black hole, and the trajectory that takes it very close to the compact object on a nearly parabolic orbit, and with a percenter that is inside the tidal radius. Here, the tidal radius being defined by the radius inside which the tidal force from the black hole exceeds the self-gravity of the star. So this means that when the star passes the black hole at such a low distance, the gas gets stripped due to the tidal force, and this results in a spread of energy or a spread of trajectory. The gas from the star does not follow the original parabolic orbit of the star, which is the dotted black line here. Instead, it follows a wide range of trajectories, with roughly half of them getting bound to the black hole and therefore returning, to pericenter in finite time, while the rest, the other half, gets unbound and just escapes the black hole's gravity on hyperbolic orbits. So there are two properties I want to highlight about this stream. The first is that despite its large radial elongation, this stream is able to remain thin in the transverse direction. And this is physically due to the fact that in this transverse direction, actually the gas self-gravity is still important, and it is really this force that is able to maintain a thin thickness for the stream, while in the other longitudinal direction, the stream is 4 to 5 orders of magnitude longer. Another property I want to highlight about this stream is its fallback rate. So this concerns the part of the stream that is bound to the black hole, and the fallback rate is really the mass per unit time at which this gas returns to percent. So this return will start after a time which I call T-min, which is the period of the most bound extremity of the stream around the black hole, given by Kepler's third law. And this period is typically of a month, which really sets the timescale of tidal subsyn events, which is a few months to years. And this fallback rate will start typically increasing, reach a peak, and later on decay to reach at late times characteristic decay law of time t since disruption to the minus 5/3 power. And this is again can be obtained from Kepler's third law. Is there any question until here? All right. So here I just want to pause to say that until that point in time, actually the gas evolution of TDs is well understood. This picture I just described has been confirmed by many methods using different numerical techniques and also analytically, even back in the late 90s. However, also until that point, there hasn't been any significant electromagnetic radiation to be detected. And in fact, most of this radiation will come from later on when this gas will fall back towards the black hole, form an accretion disk, which will emit the radiation we can detect. However, this later evolution, the return of the stream, the formation of an accretion disk, is much less understood and will be the main topic of this talk, basically. So, you may wonder why this phase is less understood. The main reason is that it's computationally not possible at the moment to carry out a full simulation of the global evolution of the gas. And the reason is essentially that if you resolve the star really well, dividing it into a very large number of grid cells or dividing it into a large number of particles, as soon as the stream gets stressed by orders of magnitude, as is the case when the star gets disrupted, there's a stringent decrease in resolution, and therefore the resolution needed to follow the process later on is extremely large. So far cannot be achieved with available computation capacity. So essentially, there are two ways that researchers have been trying to go around this bottleneck. The first is to increase the resolution or increase the computational power using such simulations, knowing that no simulation will be resolved still, at least in the near future. But here the risk is that some effects seen in the gas evolution may be due to lack of resolution. However, it contains all the correct initial conditions and everything is evolved globally, so that's a positive aspect of that technique. So the technique that I want to use is not this one. Instead, the strategy that I developed is to instead of following the gas globally using a single simulation, is to focus on the phases that we identify as the most important and study them with resolved simulation, and then assemble these different phases back together to get an understanding of the overall global evolution. So the picture I will describe here is based on this second strategy. All right, so what happens afterwards is that, as promised, the stream comes back at Earth center, and this Earth center is typically tens of times larger than the gravitational radius in blue here, or the Schwarzschild radius of the black hole. And what this means is that general relativistic effects will be important, and in particular one effect, which is the axial precession of the stream around the black hole in the plane of the screen. So as a result, a part of the stream that has now passed Earth center here has precessed with respect to the part of the stream that's still falling in. Another thing that happens at Earth center is a so-called nozzle shock, which is due to a strong compression of the stream at Earth center. And one question is whether this shock will affect the properties of the stream. And I will come back to this in the next slide. Okay, so what happens afterwards is that if everything was to happen on the same plane, due to this relativistic precession, the two parts of the stream, the part moving in and the part moving out, would collide. However, if these two planes are not the same, this will not happen. And a possibility for this to occur is if the black hole has a spin. So if the black hole has a spin, there's another general relativistic effect that happens at Earth center, so-called a length steering precession, and this effect actually changes the orbital plane of the gas, such that if the gas following in follows the plane of the screen, the gas now moving out after a Earth center passage may follow a different orbital plane, such that at that location, one stream is above or below the other, and the collision is present. Any question until here? So I will explain all the effects and then come back to them in the talk.
So yeah, I have a question.
Yes.
So I mean that's maybe something that you will mention next.
Yeah.
But most studies of TDs are done in Newtonian gravity, or because you mentioned some GR effects, or there is a mix in the literature of both types of approaches.
Yeah, so there's a mix basically, and so most studies, I would say in numbers, definitely most studies have focused on the disruption of the star and the return of the stream, but before it comes back to Earth center. And this, to study this effect, Newtonian dynamics is usually enough. There has been some studies including general relativistic effects, but they have been found not to have huge impact. For example, not to have huge impact on the fallback. You know, the rate at which the mass comes back will not be strongly affected by general relativistic effect, because essentially the tidal radius is, you know, a few tenths. At, you know, the lowest tidal radius is a few tenths gravitational radii, so it's not a strong effect. But in terms of studying what happens after, like the precession of the stream leading to this collision, there's always some treatment of GR effects, because they are basically at the origin of what causes the gas evolution later on, in particular this shock. So the main takeaway is that GR effects are not necessarily important to study the disruption of the star, but they are fundamental for what happens after the stream comes back near Earth center. Does that answer the question?
Yes, yes.
All right, so any more questions? All right. So what happens after is that if, due to black hole spin, these two stream components are not colliding, but instead they are passing one above the other, then more revolutions may be necessary, but until at some point a collision does happen between two string components, only after a delay due to these different windings. And when this collision happens, this leads to a so-called self-crossing shock that dissipates a fraction of the stream's kinetic energy, converting it into radiation energy. And due to the increase in radiation pressure, the gas gets pushed out to form an outflow, which is this spherical orange circle here. And this outflow at later times keeps expanding more and more until it completely surrounds the black hole. And in black here, I'm showing different trajectories of fluid elements inside the outflow, and you can see that they get curved due to the black hole's gravity. And from this, you might expect that there will be orbit crossings around the black hole, and this will lead to shocks, which I call secondary shocks. And these shocks will be strong enough to circularize the orbits of the gas and form an accretion disk around the black hole. And these shocks will also be radiative and emit in the extreme UV. Right, so now that an accretion disk has formed, accretion will proceed like in other accreting systems, and this will lead to additional X-ray emission. And here, in this case, the optical emission in this picture is coming from the fact that this high-energy X-ray and EUV radiation have to propagate through this envelope that is very optically thick, and by doing it, these photons get absorbed, re-emitted many times in a process called reprocessing. And when these photons eventually emerge, their frequency have decreased, and the spectrum now peaks in the optical. So this is the physical picture I have in mind for how the electromagnetic signatures from TD are produced. So now in the rest of the talk, I'll come back to the different phases, starting from the nodal shock, where the stream comes back per center, followed by the self-crossing shock when the two stream components collide with each other. And those will be studied using local simulations. And in the last part of the talk, I'll explain what happens after to this outflow from the self-crossing shock, and in particular, how it forms an accretion disk around the black hole. And this will be followed using a global simulation. Oops. All right, so are there any questions until here before I enter the explanation of the different phases? Okay, so I think maybe I'll skip the nodal shock, and you can feel free to ask me questions at the end if you are interested, just for reasons of time. Right, I will still show this picture. So essentially, what I'm showing here is that there's a part of the stream coming back and then processing, and this procession leads to a collision between the part of the stream moving in and the part of the stream moving out. And the main takeaway from this study is that the stream is not significantly affected by its passage at per center, such that we can still consider the inward going stream and the outward going stream as being very similar, actually identical. And the next step will be to follow the collision between these two streams, which can be done using a local simulation. So here, this is showing the two streams. So you have to imagine that the stream came from very far away, down, processed, below the screen, and then came back here. And this is the collision point between the two stream components due to epsilon procession. All right, so what's needed to locally study this collision is a knowledge of the rate at which mass fuels this intersection point, and also the components of the velocity of this gas, which is a tangential velocity, which is equal for the two, and a radial velocity VR, which is open. So what's convenient is to do the simulation in a frame that is moving with the common tangential velocity of two streams, essentially removing VT from this picture. So working like this in the co-moving frame, the two streams, as you can see on the right, are now moving head-on with the velocity plus and minus VR. So we did the simulation in this frame, assuming complete adiabaticity. And what we found is that, as expected, a shock occurs, and this shock leads to the formation of an outflow that is quasi-spherical and launched from the self-crossing point. And the terminal velocity of this outflow, as expected from energy conservation, is also equal. So when we boost this picture on the right back to the lab frame, essentially adding back the tangential velocity, the result is this configuration here where the outflow still expands quasi-spherically, but now it has both a net velocity towards the left, the red arrow, and also a radial expansion velocity in blue. So this velocity description is interesting because it allows to conclude that there will always be a cone of gas that gets unbound, moving towards the left. And the reason essentially is that the stream is already on such a near zero energy orbit that the additional push due to gas expansion is able to unbind it completely from the plane. And towards the other side, the green arrow, there's also gas that's moving and now on a retrograde orbit compared to the orbit of the stream. But here the main takeaway, despite this complicated velocity structure I described, the main takeaway is that there's a collision between two stream components, and the outcome of this collision is the formation of a quasi-spherical outflow launched from the collision point. All right, so what happens next is that this outflow will keep expanding, and the goal here is to use the properties obtained from this local simulation to study what happens next inside using a global simulation. So this is the global simulation, which is a radiation dynamic simulation. So here the initial setup is that the stream comes back following this dotted curve here. As I explained earlier, it precesses around the black hole, which is the white point here. And due to this precession, it collides with itself at that point. And here, the orange purple color is showing the density of the outflow from that point, which was distribution is obtained from the local simulation I just described. So here, basically, this gas is injected inside the larger computational domain to follow its evolution later on, in particular, how it would form an accretion disk around the black hole. So in that case, there's some unbound gas moving towards the left, and the gas moving towards the right is moving on the retrograde. All right, so this is what happens. So gas gets unbound towards the left, and the bound gas returns to the black hole, experiences what I called before secondary shocks. And these shocks we find are enough to promptly form an accretion disk circularizing the orbits. But there's still also this large envelope of gas surrounding the disk. So because it is a radiation dynamic simulation, one can also look at the radiation energy, which is the other movie I will show on the right. So initially, there's no radiation energy, everything is purple. This is essentially because the stream is cold, and also the outflow initially is cold because it has cooled due to adiabatic expansion. And radiation energy will be produced, will show up in yellow. It will be produced by the stem shocks that formed the disk. So that's the movie. So there's radiation energy being produced near the black hole by the shocks that form the disk. And essentially, this radiation is able to diffuse away from this production site and irradiate the surrounding envelope. Interestingly, except in this region here around the intersection point, which is screened of radiation, essentially because it's high density. So here the main takeaway is that we find rapid formation of an accretion disk, and the radiation emitted from the shocks leading to this process irradiate a large scale surrounding gas around the accretion disk. Any questions on this?
Yeah, I have a question. So when you say radiation hydro, is this so for the hydro part, is it SPH?
So it's using the code called Gizmo. So it's close to SPH, but not quite. It's particle based. But the difference to SPH is that essentially the particles are used to construct faces in between particles, and those are used to accurately, transfer flux between the created so-called cells. So it's which is not done in SPH. So it's kind of really improved versus SPH, but it is particle based. Yes.
And the radiation part, is it a flux limited diffusion or?
Yes, it is flux.
Okay, and what is the typical disk sizes that you get from that, or maybe depends a lot on the TD parameters?
So it's mostly, so it depends on the TD parameters, but what we find, which I think is general, is that the disk is typically a few or 10 times the tidal radius. So essentially, if the gas, okay, maybe I'm going too much into detail, but if the gas, actually something that has been assumed in the past is that the disk would form as a ring at a radius equal to 2 times the tidal radius, and this is what you obtain by just assuming that every single fluid element conserves its specific angular momentum. But in that case, there's actually a large spread in angular momentum. So some gas gets slightly closer than 2 tidal radii from the black hole, and some gas gets slightly further out, and then it results into this that is extended from essentially the innermost radius possible to around 10 tidal.
Okay, yeah, I get it. Thanks.
Any more questions on this?
I have one
Yes.
question.
Yes.
So would there be any emission from the nozzle shock or from the initial collision of the streams?
You mean this collision?
Yeah.
Yeah. So actually, I think I have backup slides. Sorry, I'm spoiling the rest of my presentation. Okay, let's go back. Right. So essentially, you're asking what is. So you're right that there's a shock here between the two stream components. So one might expect to have also some detectable radiation.
Yeah, that's.
And indeed, it has been proposed as a way to explain the optical emission from tidal absorption events, which is different from the way I mentioned before. So here I will explain why I think this mechanism, at least within this picture, is not favored. So basically, so photons will be produced by this shock, but then they will have to diffuse through this optically thick expanding gas. And essentially, the typical radius at which this diffusion process, they actually get trapped due to the large optical depth of the gas, and then after they are propagated to the trapping radius, these photons are able to diffuse away, and they are not coupled to the gas anymore. And essentially, the main point is that when photons are being trapped, starting from when they are produced to this trapping radius, they are actually doing work on the gas due to radiation pressure, and so they are losing energy. And what we did is to estimate the radius where this process stops, so the trapping radius. And we find that the trapping radius is typically much larger than the scale of the stream, which is also the scale at which photons are injected. So essentially, this means that this process is highly relatively inefficient. And in terms of numbers, one can estimate the maximum luminosity that we can expect from this system, neglecting any kind of energy loss. And this would be given by the heating rate multiplying the inflow rate by the energy that gets dissipated. So this heating rate is typically at maximum 10 to 44 arc per second. However, the emerging luminosity due to this reduction in energy up until the trapping radius implies that only 5% of this heating rate typically emerges as luminosity. And so when you put the numbers, the luminosity from the suppressing shock is typically less than about 10 to 42 arc per second. In this picture, where really the outflow is perfectly spherical, if this condition is not satisfied, then there may be a bit more luminosity. But really, in this picture, this 10 to 42 arc per second is not enough to account for the optical emission of TDs. So that's why it's not big.
Okay, thanks. And what about the nozzle shock? It's
all right. The nozzle shock is even worse, because in that case, even the heating rate is like 10 to 40 per second, so it's really small.
okay. Thanks.
Yeah, essentially the reason is that in that case the heating rate is quite large because the streams are colliding head-on, so it's really like almost head-on shock. But in the nozzle shock, it's more of a compression. So the velocities involved in the colliding the gas are much less. All right, so yeah, so from this simulation, one can look at the volumetric luminosity as function of time. Is shown with the black line here. So as soon as the first circularizing shocks start happening, there's a sharp increase in the luminosity that increases to about 1044 arc per second, and then increases slower after this. But the main takeaway is that this 10 to 44 arc per second is actually enough to account for observed value. So it is, in that sense, it's a good physical model for this emission. So another thing that can be looked at is the spectrum of this emission. So it cannot be directly concluded from this simulation because it's frequency average. But still one can get an idea about looking at the typical radiation temperature in the disk, which is about 10 to the 5 Kelvin. So if the disk was completely isolated and emitting as a black body at that temperature, the spectrum would peak in the extreme UV band. However, this disk is not isolated, instead is surrounded by an optically thick envelope. And we expect these extreme UV photons or X-ray photons later on to be scattered and absorbed, re-emitted many times. And in particular, we think that the presence of this cold spot here around the self-crossing shock may be important, because in that region, due to the low temperature, the bound-free opacity may be enhanced, therefore increasing the chances of these high-energy photons to be absorbed. And when these photons are absorbed and re-emitted, they would emerge as optical photons. So this is a mechanism that is the first to be proposed based on first principle simulations, but of course there are still a lot to do to make it more robust using precise multi-frequency relative transfer calculations. All right, so that's basically my last slide. I just want to give some takeaways. So I didn't talk about the first point, but I can come back to it if you want. So the second point is that we performed the first radiation hydrodynamic simulation of accretion disk formation, finding that the disk is able to form promptly, and the radiation from this formation irradiates a larger surrounding envelope. And we find that the emerging luminosity from the shocks forming the disk can produce a volumetric luminosity of around 10 to 44 arc per second, which is enough to account for observations. And finally, the reprocessing of this luminosity by the surrounding gas may be a physical process to lead to the optical emission that is detectable from TDS. So just to conclude, I hope that what I presented will pave the way to a robust model for the observational signatures from tidal emission events that in the future can be used to optimally exploit the thousands of occurring detections, making TDs reliable tools to measure supermassive black hole masses, and also learn about their origin in the early universe. Thank you.